So in the last lecture, we did discuss the microcanonical ensemble and the canonical ensemble. We discussed, and I want to repeat that statistical mechanics starts with the two postulates and one hypothesis. The postulates are time average equal to ensemble average. Time average is the experimental quantity, experimental thing that goes on, and Willett Gibbs had the main construction, the brilliant construction of ensemble. So they had to put these two together. That the first postulate, time average equal to ensemble average. Second postulate, in order to ensure that equality, that every state visited in time averaging is equally probable, or every state picked up in ensemble average is equally probable. However, one has to assure, one to guarantee that this system's trajectory takes you to all different states, and that is the ergodic hypothesis. That means every state is visited, and that is the one that has evoked a lot of research over the years, particularly from mathematicians. And the statistical mechanics starts at the level of construction of this formidable theoretical framework. The most important role is played by this relation of Boltzmann's formula, entropy equal to KBL and omega, which is often not realized that the entire statistical mechanics, the microcanonical, canonical, grand canonical, all the ensembles, everything, relation between statistical mechanics and thermodynamics is derived from Boltzmann formula. So a variant of Boltzmann formula, which is here, omega is the number of microscopic states available to the system, which is kept fixed at volume V, energy E with n number of particles. A variant of that is used to derive the second equation, which is free energy, Helmholtz free energy equal to minus Kb. Kb is Boltzmann constant times temperature, then logarithmic of the canonical partition function, and canonical partition function is given by this quantum version of sum over energy levels, or classical, that is integration over the phase space, position and momentum. What we will do today, we will go from canonical ensemble to grand canonical, then ultimately to isothermal-isobaric ensemble. So the whole derivation, remember when we did from microcanonical to canonical, we had the following construction, a mental construction. We put all the systems in canonical ensemble together, and we allow them to exchange energy, and we put them in a temperature bath, and when they achieve constant temperature, then we remove the bath and put an insulation around it, so that ensemble, the canonical ensemble, becomes a super system in the microcanonical ensemble. Then we do a super ensemble, and with this construction then we repeat the calculations that we did in the microcanonical, and that allows us to get to the result that free energy equal to minus KBT ln Qn. So today we will first briefly review the canonical ensemble, and then we will go to do the grand canonical, and we would like to finish today and discuss the isothermal-isobaric ensemble, which is the NPT ensemble, and the NPT ensemble is the one which is most commonly used in computer simulations and also very close to experimental results. You can start this essentially as a derivation, as a definition of grand canonical ensemble. This is the mu is now the chemical potential. This is a horribly mixed notation. As I said, mu and gamma gets mixed up. This would then z to the power n. I think this is one of the typos people have pointed out to me. So, and this is partly my doing, because I usually use this notation. So this was in between putting because many of the things were edited by my students. Okay. Now, what we now have to do, we have to have in this, put in the constraint, which is how I define, not the constant, how I define average number, which will define density, average volume, and what the volume is fixed. So average, if I get the average number, then I divide by the volume, which is given from supplied from outside and external constraint, I will get the density. So then I have to define an average energy, and average energy is this quantity, and pressure is, so you have to, average energy, you understand this thing, that, but now the sum, note that sum is the microscopic state or the state of the system, which is macroscopic state of the system characterized by energy Ej and number n. This is not the microscopic state, I am sorry, because it is still the macroscopic state, and because it is a large number of particles still there much of the time. Interestingly, in the grand canonical ensemble, these this is the average energy. As I was saying, that you note that they are a double sum. Now, very interestingly, the same definition we used of the pressure in the canonical ensemble, we do the same thing, but again sum over G and A. And one thing that I was going to say, which is very, very interesting property, you have to look into limiting properties of this quantity, this grand canonical ensemble. Now, this sum starts from n equal to 0. Very, very interesting. Not n equal to 1. And Q0 is by definition 1. So, the grand canonical partition function starts with 1. N equal to 0, this is 1 and Q0. That means it does not depend this. So, this is a null or vacuum state. That also, no particle in the system also contributes to the grand canonical ensemble. Now, next is n equal to 1, n equal to 2, n equal to 3. And this particular property plays a very important role, because you know, when you do these kind of sums, that calls the generating function. Whenever I put a polynomial like that, is a generating function. So, canonical is the generating function of the canonical ensemble, that becomes series. These are all positive, that is very important. And these are all positive because it is nothing but the sum of Boltzmann factors. And Boltzmann e to the power exponential is an entire function, that is a completely analytical function. This is a very important property. Since it is completely analytical function, that means this is another analytical function. You know, if you know a little bit of mathematics, one of the things, now mathematicians are not given to talk of very big language, but there is a thing which is called fundamental theorem of algebra. Unlike physicists, who very easily coin theory of everything and those kind of language, mathematicians are not at all, superlative. They are very, very reserved people. But it started the culture, initially started with Gauss. So, what is the fundamental theorem of algebra? There is a beautiful book by Lebedev. I loved it. Where is that fundamental theorem of algebra? Yeah, that's the rational approximation. That's called rational function. And that's a way to develop an approximation. We have all Bessel function and all these things. We have the rational approximation, and the book of approximations taken it full of them. But what is the fundamental theorem of algebra? Fundamental theorem of algebra is there a polynomial order n, then you have n roots, and depending if all these are positive, then you will have roots in a complex conjugate. That means one will be z, another will be z star. One of the reasons many people don't use z here is that you want to keep the z as a complex number. That's why many times, that's the reason of the confusion that two schools are there. So, it is extremely important to realize 2 or 3 properties. One of them, it starts from n equal to 0. Second, that all of them are positive, and when all of them positive, then you have these roots which are complex conjugate, and that plays very important role. You know, without that property, that will not be able to describe any phase transition or any property. Okay. Now, so then energy goes like that, Pj, and the pressure is also. So I have now definition of pressure, I have definition of energy, and I have definition of all that. Then we play the game. Exactly, we played from going to canonical, from microcanonical to canonical. Exactly, we do the same thing, this dpj, exactly the same equation we did before. But now everything is sum over j and n. There I had sum only over j. Okay. Now, then we would compare that with the thermodynamics, and we will see that this already I discussed, that Lagrangian multiplier is this thing. Okay. Entropy is generalized from Boltzmann formula, and that this one comes again and again, this variants of, that's what I said, one could as well regard it as a postulate, and this is the Euler equation. When you combine, you get the following equation, PV equal to KBT ln this thing. This is a very powerful and extremely useful thing. Now, realize one thing. While in microcanonical, I will maximize the entropy, that to find the stable equilibrium system. In canonical, I will minimize the free energy, or if I do minus A, that's the better way to write actually. I will maximize minus A, which means everywhere I maximize the partition function. So, here we maximize the quantity PV. So, PV also has the dimension of energy, right? So, in grand canonical applications, in phase transition or the things, we impose equality of chemical potential to derive our equations. Then we put the calculated pressure by maximizing this ln sigma. So then we still go on doing the relationship partition functions that we just again the same thing, we have to go to g equal to h minus ts and mu and e minus pt. So the kind of things we did in the thing is again done here, and one gets the beautiful relations of entropy. So if you have the grand partition function, you have this is the entropy, then this is the number, this should be average number, and this is the pressure. So that finishes this part. Now I'll spend some time, because this is the one that used most extensively in computer simulations, isothermal-isobaric. It was done, it was created because Gibbs, when Willard Gibbs was doing statistical mechanics, Willard Gibbs carried it out, the whole development of statistical mechanics, with an aim to understand Van der Waals equation of state. So there are those days two major approach that was going on. The people whose StatMech was in very incipient condition. One was Boltzmann trying to understand Maxwell distribution, and the phenomenal contribution was made by Van der Waals. Actually, Van der Waals is one of the underrated scientists of the bygone era. So Van der Waals had not only the equation of state, he also had a beautiful equation of interface. And so Willard Gibbs was trying to develop a theory of interface, particularly gas-liquid interface. And so as soon as he developed the ensemble thing, one of his first goal, or was the beginning goal, was to understand Van der Waals equation of state. The story is that when he did these things, Maxwell so the Willard-Gibbs, nobody knew what Willard-Gibbs was doing. He was far ahead of time. So he was doing this ensemble, canonical ensemble, microcanonical, grand canonical, even terms were new. Nobody understood. However, on the other side of Atlantic, Maxwell was keenly following the development of Willard-Gibbs. And Maxwell sent, or is the other way around I think, but they never met, but sent a solid kind of, not marble, but this kind of cement paste with a solid A of Van der Waals loop of equation of state. And Gibbs always used to go to class with the one that was sent by Maxwell. However, Maxwell died very young. Maxwell died at the age of I think 37 or 39. And within that little time, Maxwell not only did his kinetic theory of gases, he did a whole of electromagnetic theory and many other things. But well, of course, Fish is remembered for his contribution, which considered one of the most successful theory is that of electrodynamics. Now, Maxwell's equations, and then of course he has phenomenal contribution, as you know, in thermodynamics. The Maxwell diagram, SPTV and all these things are Maxwell's. So it's amazing how much he did in such a short time. As I remember, died at 37. So when he died, there is a common joke at Yale or in America that in the entire world, one person used to understand what Gibbs does, and that person is dead. So nobody. So now, naturally, these was the emphasis, the NPT, Isothermal-Isobaric ensemble. So we need to spend a little time trying to understand this ensemble. So now in this ensemble we are not allowing number fluctuations, and it is very important in computer simulation because, as I told you, this is the most suitable in many cases. We allow now fluctuations in volume. So long we have not allowed fluctuations in volume. So this is the time when fluctuations in volume is done, and that one of the reason is that if you are studying a system where, say, a liquid is going to crystal, you can simulate with the same number, but volume must change. Like water going to ice, volume has to increase 10-11%, right? So that has to be allowed. So that's why this is an important thing in study of phase transition. As I said, Willard-Gibbs did almost entire thing with an aim, and his big book where entitled Thermodynamics of Homogeneous or Heterogeneous Systems. That's the whole textbook where many of these things were done. Now, so how do we do? We essentially do the same thing again. We go on. There is a little trick of going through by introducing a Legendre transformation and using this relation, well-known relation, and then go to, which leads to a definition of Gibbs free energy, not the Helmholtz free energy. But the main thing that I want to, so the analysis goes in the same way, exactly same way we have done. But one important relation that one finds useful in analytical work is that you can consider grand partition function as a Laplace transformation of the this is Laplace term, right? So you can call volume as a time and beta p as the z, the Laplace variable or s. Then you see that one is a Laplace transformation other, and that is very important consequence, because then I can get q as a Laplace inversion of the grand canonical partition function. Now the A is that, so what we are using, one thing that, see the other notation that I use, this chapter I think probably every chapter this will come through, okay. So this is the notation we are using for both. One is ZVT, that is the canonical, and this is, I don't know who did it, whether printer did it, it's possible printer did it. and other is, the one I use is this thing for isothermal-isobaric, NPT. But here, I believe this was done by the printer and we missed it in the galley. So, but there is no confusion because it is NPT. Probably I let it go that because of the everywhere it is NPT written. So, that is why there is not much of a problem. So, what one can do by doing an analysis very similar to the one that we are doing all through, that going, then you have to do what is the average number, what is the average volume and average pressure, and then you go through that exercise. That particular exercise, as we have seen already in the case of canonical partition function, is elaborate and a little boring. So, I am not going to do that, but this is given in the book also. So, this is the final expression for, this is the isothermal-isobaric. So, advantage of isothermal-isobaric, particularly in chemistry, is that this is we get the Gibbs free energy. So, and this plays an extremely important role. Go back. It is very tempting for me to start on phase transition here, but I will not go do that here. So, this quantity, the thermodynamic potential in grand canonical ensemble and thermodynamic potential in isothermal-isobaric ensemble are, so if I do, remember G equal to, and that is E plus PV minus Ts, and E minus Ts is Helmholtz energy, right, then plus PV. So, G minus A is PV. So, PV is kBT ln ZVT, right, and G is, so I have, what I am trying to say, that we have a relation at the level of logarithmic of all the partition functions. This is then comes in isothermal-isobaric, this is the canonical and this is the grand canonical, and this is an amazing relation that is often given in slightly advanced courses of statistical mechanics that show that this relationship, you of course you are not expected to derive the whole thing, but you are expected to write down the expression of the potential. This is an amazing relation one should remember, because this is the one we use when we do Ramakrishna use of theory of freezing or density functional theory of freezing, that this trick is used. Okay, now I have discussed it here. It's very important that what is the physical interpretation then of what will let you remember and understand the partition function. I have already discussed different ensembles come with different partition function, but all of them have one common thing, is that either the partition function itself, it has to be maximum. So, the state that is selected, or the state that is thermodynamically stable, is the one that has the maximum partition function. Now, you can understand that physical insight from canonical ensemble. Why? Can anybody tell why canonical ensemble? Every ensemble gives this beautiful interpretation. But why in canonical ensemble, this is particularly enlightening and very, very intuitively clear. So, partition function I can write right. I can also write in some normalization, which I am not going to talk now, all the particles, all the momentum and e to the power minus beta h. H is the Hamiltonian. Right? I don't remember giving these equations to you when we did canonical ensemble. So we start with grand canonical, allowed fluctuations, then how did the logic go? We started with microcanonical, then we relaxed that. We constructed the thing, and then, oh yeah, we did that because that is what was done in normalization, right? I explicitly, separately, this I wrote down, but classical version I did not write down. This is the classical version. Now what I am asking you, we already discussed that Qn for all n, Qn is positive definite. That's a very important quantity because they are the coefficients in the polynomial that defines grand canonical partition function. Now I am asking you a question that it is intuitively clear in any of this definition, is most clear in this ensemble, not even in microcanonical. Why a partition function, maximum partition function, selects the macroscopic state? Not that, I am asking something very simple. It is trivially simple, but you need to think that a macroscopic state which defines the equilibrium or the stable state, because that's supposed to be stable for time t goes to infinity. Why that is partition function is maximum? Okay, see, just I give you a simple example, and now you should be able to tell. I have these two. Which one will be selected? Why? There, Baba. That because this is where this is maximum. If I have just two states like that, then this still has certain contribution. But I have, say, infinite number of particles in my system, macroscopic. Each particle is little stabilized. Then this just disappears. This is selected. And that comes from this expression. That it is the energetic criteria which we intuitively understand from our Boltzmann distribution is included in the partition function. And that's exactly, this is very, very important that I am telling, because that's how selection is done. Absolutely, zip, it just goes through. To keep in coexistence, particularly in computer simulation, is extremely difficult. Even in computer simulation of 1000 particles, this, what I am telling here, becomes very important. Okay, so let's continue. These are very, very intuitive and very nice. So you have to understand, I remember when I taught and gave exams, we should do some problems. So now that what I have been telling is that these are the functions. So for a given thermodynamic state, read this, and the partition function is maximum at equilibrium. This is a very important thing that no StatMech book tells you. Let us elaborate this and the often quoted statement to gain some physical insight. Then I describe, consider physical quantity. It can be function other than the state functions. Then all these quantities are satisfied. Very important, because when you try to expand a free energy, like in Landau theory of phase transition, or any kind of thing, that the first derivative goes. So the order parameter, zeta is the order parameter, I mean the parameter that distinguishes between old and new. That we'll discuss in detail. This condition is very important. So the first term, and if there is a symmetry, then third order term also not there. So that's why this is the reason why the free energy function for small displacement is harmonic. Is an extremely important quantity, because the coefficient of the harmonic, the force constant, are what we call the response function. So specific heat, thermal compressibility, all these things are the second derivative of these quantities. And that is the reason in a phase transition, these quantity will become the harmonic frequency goes to 0, because the springs, we call the response functions of the springs, and they soften up. It's a very beautiful thing that going on there. So then, as I am telling you that there are, so these are the cartoons, microcanonical, then canonical and grand canonical, that kind of thing. My students I found are very good in cartoons. And so there is a problem set. I have to imagine somebody has to do the problem set. Okay, so these completes the A on canonical answer on the partition functions. Next, what we are going to do is to start on the next chapter, which is the, okay, we have two ways to go from here, but I would like to really jump the board little bit and do something very interesting, which is this, the response functions that we have been discussing. That means which are in terms of fluctuations. So the response functions are second derivative of the free energy, like specific heat and compressibility, but their real meaning is that they are the quantities which are the standard deviations or mean square fluctuation of the relevant quantity. So the idea is the following: we will do the response function or fluctuations. Chapter is, I think, chapter 5, chapter 6 is fluctuations in the book. After fluctuations, because it is so important, I want to do it next. After fluctuations, that was done by Einstein. After fluctuations, we do monatomic gas and diatomic gas. All right? Okay, thank you. Right, very good question. NPT simulation. See, the way when simulation happens, if you plot the pressure, you will find that even with the barostat, which is slightly fluctuating, but we define it. It has to be on the average the pressure in your piston, which is barostat. So it is not correct to say absolutely not fluctuating, but it's fluctuating very small amount. The one that is fluctuating is the volume. Volume is fluctuating in a big way, but you can still define a volume, and the mean square volume fluctuation, that gives you the compressibility. Absolutely, yeah, absolutely. The thermodynamic properties calculated in ensemble, every ensemble is all the thermodynamic properties are the same. That because one can show, we'll do little bit in the energy fluctuations. Today afternoon we'll do that. The fluctuations or mean square fluctuations. See, what we need to talk of the quantity, and then how it is varying with n, and or the fluctuation in the quantity. That you can show it goes as 1 over root n or 1 over root v. So n going to infinity. So you start the microcanonical ensemble, no fluctuation is allowed in E, N and V. Now I go to canonical ensemble, I allow fluctuation energy. Now I calculated how the fluctuation energy goes. It will go as 1 over root n. Now I go to grand canonical, I allow fluctuation of n now. Now I calculate how the fluctuation. So the result that you get at the fixed in the microcanonical ensemble becomes the same at canonical ensemble, the same at grand canonical ensemble. Calculation of properties in microcanonical ensemble is essentially impossible. It's extremely difficult. That become progressively easier, and that we'll discuss. that because, this I think you got to, you need to love mathematics to do stat math, because statistical mechanics is a very mathematical subject. I was going to tell and I forgot, because I usually do a random walk in my teaching, but all through these years, my students, not my own students, my students who took my course, always, they say they enjoyed and remembered this little bit of random walk that I do. So I tried to tell, that is where I came to tell you the fundamental theorem of algebra, that grand partition function is a infinite series, is a polynomial, but it is a series, because up to infinity. However, you can pack only certain number of particles because of the Hart-sphere kind of interaction, short range interaction. So n equal to never infinity, it becomes a maximum value. So it becomes a polynomial. So when it becomes a polynomial, then it has zeros. Zeros of the polynomial determine the singularity of the partition function and properties. And those are the things called very famous. We will do that. I have a chapter, I think chapter 13 or 14 in the book, which called Youngly theorems. And that was exactly that very, very famous contribution by C.N. Young and T.D. Lee, who got Nobel Prize for quark confinement. But this was also one of their phenomenal contributions. Has to be. Think of putting a marble ball in a jar. You can put only a certain number, because after that you cannot pack. So we'll come back.